Right, adaptable structures. I should introduce myself to begin with. My name's David Knight. I'm the Vice Chair of the IStructE Structural Futures Committee, and I was also the Chairman of the IABSE Henderson Colloquium in 2018. The Structural Futures Committee is a panel that the institution hosts and runs to look at the future of the structural engineering industry, and we have regular meetings to discuss what might come up in the medium and long term. And one part of that is to keep looking again at the codes, keep looking again at what we as a structural engineering community can offer and how we can change that and how we can make that better and more efficient. IABSE, on the other hand, comes at the process from a slightly different direction. It's the International Association for Bridge and Structural Engineering. It's an international organisation, as the name suggests, that looks to gather people together to discuss topics of interest. And the Henderson Colloquium is one of those events. It's been running since 1975, hosted by the British Group of IABSE, and it's a two-day event in Cambridge often for about 25 people who are invited to discuss a topic of importance. This year's theme was on adaptable structures, and particularly on how we adapt structures to cope with serviceability criteria. Design for serviceability, as we know, often governs structural schemes through the codified use of general rules, maybe span to depth ratios, deflection ratios, frequency limits, and it can often create a general rather than a specific solution. These rules are a baseline. They often don't fully account for the realities of user comfort and perception. What the colloquium was looking at was whether, with the advent of new technologies and new ways of going through the problems involved in serviceability, whether we can start to answer some questions and possibilities that arise. The brief was set with a series of questions, and I'll just run through those now. For interest, these were the participants in the event. There's some familiar names there. There are some IStructE gold medalists there, but there are also representatives from across the industry, both as clients, as consultants, and as academics from a range of disciplines. So the questions we were looking to answer included: can increased monitoring of existing and new structures provide data that allows for alteration of the rules that we currently apply to SLS? Can modern data analysis techniques allow us to update load factors on a regular or live basis based on current information? Can adaptable structures accommodate varying comfort requirements over a short time frame? How good are we really at predicting the future use of our structures? Can we design structures so that changes in use in the long term can be accommodated with simple structural modifications? How do we weigh the future flexibility of space, i.e. the future unknown, against the built embodied energy, which is a way of saying the current cost? How well do we understand what governs serviceability, and should this be a driving design? And how does the difference between, say, the assessment codes and the design codes reflect what is easiest for the design process, but maybe not efficient structures? And, of course, what prospective new technologies are there that may improve serviceability performance? Ultimately, we're looking to see whether there is a new family of structures that are designed for a first use load case, have a lower embodied energy, material use, construction cost, are designed for flexibility, but future use is not necessarily prejudged. We'll be able to accommodate new technologies and perhaps also contain monitoring to improve the global understanding of the performance and are really truly adaptable. The colloquium went through these questions and were challenged by them, really. A lot of the things that I've mentioned require a lot of in-depth work and a lot of in-depth thought about these issues. We've gathered together some people here this evening, some of whom were at the colloquium, some of whom are related otherwise, to to set the scene, to bring their perspective, and then we will open the floor up to discussion. The majority of the evening is an opportunity for a backwards and forwards between the panel and yourselves about the issues and some thoughts, with the aim that by the end of the evening we can come to some conclusions and maybe suggest some directions for research, perhaps, if we get to that stage. We have 5 panellists, in fact 4 panellists and a chair. I'm pleased that Ian Firth, who's the chair of the IABSE British Group, will be chairing the discussion and prompting you for questions. Ed Clark is on the panel. Ed is a director at Arup and also the chair of the Structural Futures panel, so he brings both the view of the institution but also some of the work that Arup are doing. We have Neil Loudon from Highways England with a client's perspective on serviceability and assessment and the issues of the day. Michal Drewniok, I apologise, Michal, from the University of Cambridge, who is an academic looking at the impact of use of structures and how we might approach that end of the issue. And Will Algaard, who is also from Arup and is a consultant designer and has worked on some fascinating structures that he will show us and talk about his approach. Each of the panellists has got about 5 minutes to start. We'll try not to time them, but I may cut them off. And then we will get over to you, and Ian will seek your questions. So let's welcome Neil first as a representative from clients.
Well, good evening, everybody. I started the Henderson Colloquium with posing quite a lot of questions. David has already given you quite a lot, and I intend to do a few more. So we're all very familiar with the structural approach to serviceability and the things that are important. David's alluded to some of those. And really, for me, they're obviously important as a client organisation, but actually one of our imperatives at Highways England is really around customers. So one can see a lot of those as being really important to our customers, in our case, road users and those people who are neighbours onto our network. But in order to satisfy those serviceability criteria, there's got to be serviceable and perform its functions throughout its life. And we tend to focus a lot on new design, and that's fine, and you'll hear from further speakers about that. But it's important, it's through life. So do we need to look at that through life more from an asset management perspective? What really is working life for a structure? And obviously it depends on the nature of the structure, and it can have many changes throughout its life. Environmental conditions can change, climate change is important, extreme weather conditions, I gather it's happening out there at the moment, so but customer expectations change as well over time, and that's really is important. We have to think about lifestyle changes. Autonomous vehicles are on the way. Platoon vehicles, that and looking at loading on our structures. Work patterns changes, fuel availability, different types of fuels, all these things are important. And as David has said, technology as well. So where does the technology in terms of monitoring our structures come from, given that we have large asset bases, in our case over 21,500 structures? We need to look at the financial side of it, and we need to look at the people side of it, having that knowledge and expertise, not just in new design, but in managing our structures as well. But of course, many of our structures, in our case, are already built. So what does serviceability mean in that case? So do we need a different definition? And things that can factor into this is, and this goes right back to the start, the quality of the construction in the first place. And I'm sure we can all think of examples where maybe the quality has not been as good as we hoped. So what are the fundamentals of that? So we need to have really good records. We need to do our inspections of our structures. We need to do investigations where necessary. But do we really understand deterioration of structures and the changes in condition? I suspect is an area we need to improve on. Do we understand the residual life of a structure? And all this leads into how we intervene with maintenance and repair strategies for our structures. So Do we understand that and the effects that we can have on the structure when we do intervene? And really, fundamental things, well, what does safe really mean? And what does fit for service mean? So one of the areas I'm particularly keen on is learning lessons. And you will all be very familiar with these and things, tragic incidents such as Grenfell and Genoa and the 4 or 5 structures that have collapsed since Genoa, Calcutta, Canada, another one in Italy and in Russia as well. So there's a lot of collapses going on. So what things can we learn in terms of how we manage our structures going forward? And we need to embed those lessons back in. So, you know, I'd advocate organisations such as Scott and Cross, particularly here. So one of the other areas, features to think about here is, you know, when we have designs that are really cut to the bone. So what does that have, what sort of effect does that have on serviceability and the capability to be adaptable in the future? We need to think about the material side of it, you know, having materials that are more durable. We need to have good knowledge of those materials as well. And we are thinking about things like rapid construction, accelerated bridge construction, those kinds of things, modular, prefabricated construction. But what impact do they have potentially on serviceability and that adaptability? So adaptability, ease of modification, and then future-proofing, what really lies ahead. So we've built lots of things in the past. Some of them have been good. Some of them have been not so good. Some of them gives us lots of challenges about how we actually manage them and modify them. And I'll give a couple of examples there. But, I mean, some of the challenges around the post-tension construction, and that links back into Genoa as well, are really important. So how do we anticipate those future needs? It's really tricky. We may want to demolish. We may want to move in some cases. We want to widen, lengthen, or even raise structures. So all of those things are important for structures. And then we have the users of the network as well. So traffic patterns, traffic levels, changes of use, changes of role. And of course, in the case of bridges, there are 2 main users. I might talk from a Highways England perspective, but our structures cross or are crossed by somebody else who's got other responsibilities. So we need to think about that as well. So I've whistled through that and hopefully stuck fairly well to David's 5-minute timescales, but really there are questions there and to help promote the debate later on. So it's a thank you from me, and I will sit down now and hand over to Michal.
Thank you so much, David. Welcome to everyone. Warmly welcome for all of us, all of the people who are watching us. Hello. My name is Michal, and I'm representing the Department of Engineering, Cambridge University, and I'm involved in the project which is minimizing energy in construction. And I found some very interesting things about the serviceability and adaptable structures topic. But first of all, some driver, which the main driver which drives the thinking about it. So nowadays, the buildings and the construction industry is represents about 40% of CO2 emissions. We are going to increase the population. Our goals is to reduce the emissions, and more than 2/3 of people are going to live in cities. And therefore, in 40 years' time, we are expecting to build 230 billion square meters of construction, which is equivalent to building Paris every single week for the next 40 years. It's huge. We have a goals that allows us to reduce the operational energy. However, in the next couple of years, by the 2050, we are having all energy which is connected to the construction is going to be from the embodied energy connected to the materials. And that's why I would like to short introduce the project which I'm involved in. So the MICON, which is Minimizing Energy in Construction, led by John Orr in the University of Cambridge. So our long-term vision is for the built environment to be designed effectively, based on a whole life cycle energy consumption using minimum material resource for appropriate performance. That is very interesting thing to the appropriate performance. So in general, we would like to look at the practice, what requirements are in the practice, how we use resources, what requirements should be met when we like to meet the appropriate performance, and then have how we can minimize the energy in construction. So we are looking at the serviceability as well. And for us, we are looking at serviceability in case of fit for human occupation, so SLS, well-being, health and well-being, spaces building, as well as we are looking also at adaptable structures, and also in the future about more active structures. But current study shows that that is the graph which shows the utilization ratio of 27 different buildings in the UK and more than 3,500 members. And we found that the targeting of the utilization is 80%, so 0.8, rather than 1%, where 1%, which is the maximum allowable performance value. So if it's 1, you can reach the value which is above, it's not acceptable. But we found also that usually in 60% cases, serviceability governs the structure. So what should be also mentioned that this study is taking into account the higher load that code requirements are. So if we have lower value according to the structural codes, we would have even less inefficiency. So material utilization might be much lower if we take into consideration the real life load requirements. So Eurocode says that life load for office space is between 2 and 3. It differs in the different countries. And last year, because we tried to find how the practice runs, so we tried to find what is the 60 years average by the experience. So we asked structural engineers. So the 60 years average, we found that it's something like 2 kilonewtons per square meter. But at the same time, we asked the structural engineers what is the 60 years maximum, and they claim 1.5 kilonewtons per square meter. It's allowed life load, only floor life load for office space. London office buildings are usually designed for 5 kilonewtons per square meter. So every single square meter has to be filled by those people. Is it possible? I don't know, maybe. Now I'm trying to find more about it, and I try to find the experiment of that in my university. Research which was made in 1893, so it was 120 years ago, it also states that it's impossible to have that kind of load in the building, that kind of load. In average, it's likely the average is about 0.3, 0.5, definitely below 1 kilonewtons per square meter. When we compare some other discipline, and if we take into consideration the office building with 16 floors, 3,000 square meters, we can find that for the ventilation requirements, we can have 3,000 people in the building. According to BCO guideline about the occupancy, we can have 3,775. For fire design, 7,500, and for structure, it's more than 85,000 people, and that gives you all the requirements for the 3 kilonewtons per square meter, so the upper boundary of the code requirements. I'm not talking about 5 kilonewtons per square meter, which London buildings are designed for. More information you can find on the website. What is very interesting about flexibility, adaptability, and everything? So BCO guideline specification claimed that historical buildings are usually over-specified according to life load. That's fine, but it becomes a standard to the current design. And they claim that it might, that is the perception, that it provides a degree of flexibility. I don't know what does it mean, because I didn't find anything about flexibility and requirement about flexibility. Of course, flexibility and adaptability, they are all, as it was mentioned before, we don't know exactly what adaptability, flexibility really means. So what are the requirements? What should be good to design more flexible or adaptable buildings? So that's why we're working on that now. And you can find more about our project on our website, on YouTube, IStructE. There was 1 month ago, there was a lecture here. And also I have some reports, if you like, I can share with you. Thank you very much.
Well, hopefully this is a little bit of a contrast to Michal's talk, because I feel quite strongly that structures should be designed for 100% utilization, not 80%, and I also feel that they should in general not be designed for service criteria. So I'm going to try to elaborate a little bit on that. I think we are at times maybe a little bit too lazy to take a too low risk approach. And are not willing to push the boat out, so we comply with service criteria that are not particularly well defined, not particularly helpful, sometimes misleading and actually sometimes plain wrong, and often send us down the wrong path. So my view is that we should work harder to try to understand the core of these service criteria. And by the way, when I talk about service criteria, this is strength and deflection and vibration in structures rather than serviceability and maintenance of structures that maybe sort of Neil alluded to a little bit. So this is a different thing. I work with architects who tend to always push for a minimal structure, and as can be seen in some of these examples, that doesn't necessarily push you down a route where you can have a purely strength-governed design. But I believe in general, when we should configure the structure so that when designed for strength, it will also satisfy the serviceability criteria. Of course, there are exceptions to this, and there will be some, and I was talking to Ian earlier about some where actually strength doesn't come into it, which maybe we'll get back to. But in general, I think this is an approach that we should think harder about. And we should push our collaborators harder to pursue this approach. When I say collaborators, I mean architects and also facade contractors, facade designers, others. You will see in a minute. Anyway, this is one of the examples. This is a bridge in Chicago with Renzo pianos, which is very slender, span to depth of 45. We looked incredibly hard at the dynamic performance of this, and this is actually within the typically accepted criteria by a factor of 4 or 5. But even so, that doesn't necessarily guarantee that all users feel comfortable using the bridge. This is another example. This is an art gallery in Santander in Spain with a series of very lightweight cantilevering walkways, cantilevering over the sea, and we fight gravity very hard. But even once we've done that and think we've won, we still got to deal with inertia and dynamics. And there's two sort of cantilevers that I'd just like to talk a minute about. So one is quite a long one, 9-meter cantilever, and this one is damped. We put in an architecturally expressed damper hanging underneath. The other one actually is the interesting one. This is only 4.5 meters, but if you do the calculations that we tend to do for dynamic response, we'll find that this is something like 10 times over the limit. But nobody is worried at all. This feels perfectly comfortable, completely normal, no big deal. But both of these are pretty indulgent structures where it's hard to argue that serviceability criteria are not a significant driver. Tall buildings is another matter. So the difference between a well-designed, efficient, tall building, and one that allows serviceability to govern. Could be thousands and thousands of tons of steel, tens of millions of pounds in construction cost. But the interesting thing is that the criteria that people use around the world vary widely. So having worked on tall buildings, both east and west, you realize that there's a huge difference, and sometimes nobody really understands the drivers. So in China, one tends to have to comply to a deflection limit of height over 600 or 800. In London, maybe we use height over 500. In Korea, we successfully negotiated height over 300 to 400. And in Taiwan, height over 200 is a perfectly normal criteria. You know, that's just what they do. That's in the code. You know, this place sees typhoons, it sees earthquakes. You know, anything stiffer than height over 200 would be pretty hard to do, and therefore they just get on with it. No big deal. And when you try to enter into a discussion or negotiation about the criteria and what they really mean, why they're really there, you often find that people aren't really very willing. So in relation to facades, which is the normal first response you get, we can't make it that flexible, the facade can't take it. Facade contractors, facade consultants are very often, and architects, often not interested in the mode of deformation. So if it's a flexural response, that just means an opening and closing of a stack joint at between the stories. If it's a shear response, it's a very different matter. It's much more complex mode of deformation, and depending on the facade system, it can be much harder to deal with. But this doesn't form part of the typical criteria. So we worked with our facade team, and they've developed an app which really allows you to distill and extract from each mode of deformation what the impact on the facade is. So this is actually a live thing where you can slide things left and right, and you can allow things to move. I didn't want to take the risk tonight. No, well, I'll need to log in. It's all, it's not that easily accessible. We could try afterwards if people are interested. But so this is just showing the static system, and then you apply a bit of floor load onto these two stories. You can look at the effects on each joint, and then you can apply some drift onto this, and then you see what that does. And depending on whether it's a moment frame type structure or a core structure, they should also add a braced frame structure here. I'll talk to them about that. But you can really understand exactly what drives this, and it's not well enough understood, and people are stiffening up buildings in ways that really aren't needed. So my view is no, we shouldn't add any material for service. Thanks.
Right, so I'm up last. Adaptable structure. So I'm going to take a slightly different perspective on this, and I wasn't at the colloquium, so I'm perhaps a little bit behind the curve on the conversation compared to my fellow panellists. So adaptability can mean a number of things, and of course in this context it's linked to the idea of serviceability. And one approach might be to just not deal with serviceability, perhaps sort of along similar lines to Will described. You could just let your structures move a bit more, let them bend, and it seems to work pretty well in the natural world. But sometimes there are good reasons why we can't allow that in the structures that we design. But again, I was slightly surprised to see some of Michal's statistics, because for me it feels like, as a building designer, as a structural engineer, that for most of the structures we design, we design for strength, and then we check for serviceability. And I think if we've got our diagram right, and we have a good structural conceptual scheme, that often that's okay, and we don't need to add more material in to deal with the serviceability requirements. And I think as an approach, I totally endorse Will's view that's the way that we should think about approaching our structures perhaps more often. But there are some types of structure where serviceability will play an important role. Very slender structures, long span bridges, tall buildings, where sometimes we may need to do something more to address serviceability. And you know, there are sort of three, in sort of trying to distill it down, there's sort of three ways we typically deal with that. We can try to modify our design to change the geometry or the topology of our structural design to make it stiffer. We can add more material into our design to make it stiffer. Or if the problem is a dynamic one, we can add damping in to get acceptable sort of performance in service. And these as techniques have served us well for many, many years, even adding damping to our structures for over sort of 50 years, 40, 50 years. And it's allowed us to design and construct some incredibly elegant structures. But there's still a fundamental issue here, for me, where there's room for improvement, because in all of these structures, we only ever have one design, but a design that has to cope with, theoretically, an infinite number of load cases. And so my question is, can we do better than that? How do we do better than that? Now, as an industry, we're all aware, some of us painfully aware, that we're going through a sort of digital transformation, and there must be ways that we can use this new technology to address this fundamental problem. But what would that look like? So, could we, for example, make better use of sensors, data, algorithms, and actuators to allow our structures to respond in real time, to change their geometry or to change their damping to follow changes in loading conditions? This is a sort of experimental kind of example of that. This is by the Institute for Lightweight Structures in Stuttgart. It's a timber shell roof that changes its geometry to respond to different loading. But is that a bit far-fetched for kind of real structures that most of us spend most of our time designing? Well, I don't think we're that far off. So, you know, in some of our big infrastructure projects, we use sensors to monitor the health of those structures through their life. Sometimes in our research, we use sensors to understand how our structures really behave, and that helps us to evolve our design methods and feed back into the codes. This rather unglamorous photo is the piling at the Exhibition Road extension to the V&A project, which was completed last year, where we worked with Cambridge to embed some fibre optic sensors into the piles, which were tension piles mostly, to help us understand how the strain develops in those piles over time, so that we can really understand the soil structure interaction, in the hope that in the future it will allow us to design our piles more efficiently. So we're doing quite a lot of this already, but maybe there's just a feedback loop that's missing that allows us to take this data and not just use it to improve what we do in the future, but to use it to change the way our structures behave or the way our structures are used right now. We're a bit behind the curve in this thinking, I think. Our building services mates are streams ahead. So there's a lot of buzz in the industry at the moment about using environmental performance data in buildings. A lot of our clients want to know how their assets are performing, existing buildings. And a lot of talk about smart buildings, smart controls to buildings. And even in our homes at a rudimentary level, for years, you know, the thermostat that controls our central heating system, the alarm that goes off when too many people in a lift, for example. These are all examples of this type of approach that we don't yet really use in our structures. And maybe we think, well, you know, we're a bit wary of this as structural engineers because the consequence of failure of a control system for an adaptive structure might be a bit more significant than my central heating system not working quite right. But, you know, how different is it to the way that an aircraft wing changes its geometry and changes its shape during takeoff and landing? There's some fairly serious consequences if that doesn't work quite right. So I think this is nearer than we think to being a reality, is my point. This is a building that Conrad in the audience knows very well because he designed the structure. But I want to talk a little bit about the shading device on the outside. So these are the Mashrabir active shading system around this building. They're quite big objects. They're not primary structure, but they do open and close in response to the sun as it tracks around the building in real time, responding to that sun data. And you know, okay, so they're responding to environmental performance data rather than structural data. But projects like this signal to me that you know, we're really, if we take this technological approach, that we're really not that far off producing a new generation, a new breed of truly adaptive structures.
Thank you to everybody. I'll ask the panelists to come to the front now, and I'll hand over to Ian to share the rest of the evening.
Right, let's grab some water first. Good. Well, thank you so much to the four of you. Fantastic, really sort of thought-provoking, stimulating stuff. Looking for someone to put that down. I have to move a mouse. Hold on a second. I'm hoping now it's your turn. You've got some things to say and make my life easy. So all I've got to do is stand here. So go on. Yes, there's a hand up. Go on. You start with a question. I was going to fire away, but you could please go first.
I'll apologise first off because this question might come a little left of centre. But if I explain who I am, you might then understand the question. So my name's Wallace Swan, and I'm from a company called Michal, who manufactures steel. And as a company, we're trying to do kind of our bit with some of the things that you've described and outlined in your conversation there. And one of those things is that we're kind of hell-bent on producing higher strength steels, thinking that that's what the market wants. Do you think that's aligned with the sort of things that you've talked about this evening?
Will?
Absolutely. I mean, especially in tall buildings, which should be governed by strength, smaller columns, less material, less carbon. Yeah, it's got to be a good option.
Oh, it's a very interesting question because in the bridge world, which is where I inhabit, it's going the other way largely because people want stronger materials to be lighter weight because we're designing for strength. But we're not talking about designing for strength. We're trying to design for serviceability, in spite of what Will says. Ed, down your far end, what about your views on higher strength materials? Is this the way to go?
I think there's certainly scope for higher strength materials in some of the structures that we design, or maybe parts of some of the structures that we design. So if we're talking about long-term adaptability of buildings, there are bits of our structures that are kind of easy to strengthen later, beams and slabs and things, and there are bits of our buildings that are hard to strengthen later, perhaps like the vertical, columns, cores, foundations, and so on. So if we can use higher strength materials perhaps in those areas of buildings and accept there's a little bit of overcapacity there for most of the life of the building, it will provide, for not very much initial cost, that longer term flexibility. So I think there's certainly room for higher strength steel and concrete.
Exactly, and just to talk about the concrete for a minute. So if you're building a super high-rise building, self-weight of the columns and the vertical structure itself becomes a fundamental driver. So a lot of these super tall concrete buildings would not be possible with concrete weaker than 80 or 100 or 120 MPa.
I think there was one thing from me, and I'm sorry to keep labouring the theme about in-service, but some of these materials, and we've certainly been looking at ultra-high strength fibre reinforced concrete recently, is around the knowledge about those materials and how they perform over time, and having that understanding. There are certain codes around for some of these materials, but in some cases they are beyond the current accepted codes as well. And therein lies a problem, doesn't it? The sort of natural resistance in our notoriously conservative industry to adopt change until it's been done for the last 50 years, Who wants to ask a question? Yes, please. Thank you. I'm interested to get to a point. Please hold your thoughts just for a second, but just to sort of put some thoughts out. I'm interested to unpack some thoughts about the economics of adaptable structures, which would be interesting just to sort of think about that, and the relative economics of going to higher strength and therefore potentially more expensive materials in order to achieve a better performance. But please, fire away.
Hi, good evening. Conrad Europe. First of all, I congratulate all the panel speakers for the presentation. I'm passionate, especially on the topic Ed mentioned towards the end of the session on monitoring of structures, because I've done research in this topic. I think one of the main challenges is the reliability of the data, especially, say, in the piles you were mentioning for the V&A. Their calibration, how, if after 10 years you're getting this data, but how can we ascertain that the data is reliable because we're going to be taking important decisions based on that. So I think that is one of the main challenges on this technology.
Sorry, I'm going to labour that theme of mine again tonight. I mean, the challenge for us is, I mentioned we've got 21,500 structures now there. So most of them are there. We are building some new ones and some significant ones, but actually most of them are the ones that are out there. And it's the application of technology to those structures in my case, and that's an issue for us. So, you know, the challenge is which structure or structures, what part of those structures, and then it's picking up your point about calibration. So how much deterioration has already occurred in that structure before you put the monitoring in place? So it's retrofitting of technology.
I think this is an interesting distinction, isn't there, between the management of existing asset, which of course Highways England has got a major issue with, because the number of new bridges and structures being built is tiny by comparison with the number that they're having to look after on one side. And of course, the development of new structures, and we see around the cities of London and elsewhere, new buildings being put up all the time. And I think most of the conversation we've been having so far has been about the new buildings. Where's technology taking us? What are we going to be able to do in the future, or even now, with new structures? But these two things are very, very different, aren't they? Reliability is everything. So our responsibility is to learn from the past and from the lessons of people like Neil and those who are managing and looking after existing structures. We've got to learn those lessons so as to be better in the future. Michal.
Sorry, can I just...
go on.
Sorry, I just wanted to address one aspect of Conrad's question on the data. I mean, we talk about using big data these days, so analysing big data to make decisions. And lots of other industries do that and use that as their kind of sole mechanism for predicting future performance. So perhaps we should be doing more of that. But to do that, we need enough of it, right? And I think the problem that we have is that there isn't enough data that's openly shared within our industry to allow us to draw those conclusions. So learning what our fibre optics are doing on a handful of piles in one building, I agree, in isolation is not enough to make a change to the industry. So somehow we need to be collecting more data, and somehow we need to be sharing it more openly if we're going to actually make this work.
It's a really important point.
I totally agree with that. If I may just add something. The data now, it's very hard to get in general in the construction. When we started our first project in the University of Cambridge, we have very limited data sources. So because we got a project with the industrial partner, we could have the data from him directly. But for now, for the last couple of months, we tried to get any data of existing buildings. And I will be very happy to see the buildings with a utilization ratio of 1. I'm extremely happy, and I could say we are wrong. And I would love to say that we are wrong.
But I think, because this is sort of slight deviation.
Go on, go for it.
Just for a second. I think looking at element utilization is not necessarily the most clearest and intuitive approach. What you've got to look at with a, say a tall building, how much material is in it and how much can you take out? If you tried a little bit harder, can you take out 1,000 tons of steel, or couldn't you? Using the same strength, right? Yeah. And my view is that we should be at the point where it's down to the last few percent, which are there only for rationalisation and constructability.
But would that impose some limitations in the use of that building in the future?
No,
shouldn't do.
No, because it's all, as Michal was saying, it's designed for so much load anyway.
Because very largely, I mean, even on bridge structures, the material is not often where the durability issues happen. It's in the joints and the bearings and things and so on. So reducing the weight of the material is not necessarily going to be the thing that leads to problems in service. Angus?
Yes, I'm not sure we've heard very much about what I would regard as adaptable structures, in that adapting means that, in my head, it means that you build a structure and then suddenly the load changes or something and you have to adapt the structure. Quite different
actively adapting on its own.
Well,
responsive.
Neil has just told us about your 35,000...
25. You exaggerate slightly, 21,500.
21,500 bridges. Now, I mean, I do know that when we joined the Brex in rather than Brex out, we had 32-ton trucks and Europe had 40-ton trucks. That resulted in a lot of structures being adapted. So a lot of your 21,000 structures have already been adapted. And it's quite interesting to sort of hear a bit of story about how effectively that adapting took place and how much people are thinking. Our geotechnical friends have a phrase that I've forgotten now, but it means suck it and see, which that you don't spend
observational method.
Observational method, that's exactly it. Thank you very much. Observational method, where you don't spend too much money at the beginning, and then you see what happens, and then you have Plan B. Have in your 2-day colloquium, did anyone sort of start thinking in those terms?
Well, I mean, I can say yes. In terms of the discussions about structures which are adaptable in the way that you describe, in other words, you can come along and strengthen them, or widen them, or do something to them. I mean, I think, you know, that's one kind of adaptability, and I think most of our structures actually are adaptable in that way. Maybe it's not so easy in some building structures because, you know, you can't take some elements out so easily. But who wants to comment on that? Ed, do you want to pick up on the question of adaptable in the sense that Angus means?
Yeah, I suppose as someone that's involved in building structures and quite often building structures in say London, for example, when if you look at the commercial office market, or you know the desire to go from take buildings and translate them from commercial office to residential and back again, and you know depending on you know how the market's moving, having structures that can be adaptable in that way, I think is really important. And again, I'm sort of slightly different to Michal's experience of just completing an office building in Paddington at the moment, where a tenant is coming in and wants to take a whole floor but turn half of it into a gym, and so you know it's a completely unexpected change of use. And I think if you don't allow some flexibility for that sort of thing, then the building is not kind of serviceable.
I think
anything that you know when we're going to need to do more and more building reuse, right? So anything that can prevent us from having to knock down buildings that are only 50 years old to put something back that's actually very, very similar, but just not quite. You know, that's the sort of thing.
That's been surely a design criterion for as long as I can remember. I mean, the need to design your building, from a structural perspective anyway, to be adaptable. So, you know, think about how the services might need to change in the foreseeable future. Of course, what's happened is that the foreseeable future has become very short because change has been so extraordinary. Yeah. I'm not a building designer. Who wants to comment on experiences you've had of designing a building for what you thought was going to be adaptability, but actually have found in a very short space of time that it's not? Anybody had that experience? Okay, you're all designing. You've got better crystal balls than some in that case.
Not turning up anyway.
Not admitting to it. Yes, at the back, please.
Thanks. Yeah, I can actually think of one structure that I had designed with a simple thing, just having soft spots for stairs. And I suppose to think of an adaptable structure, there was provision for stairs to be put in, but a new opening had to be cut directly beside this stair opening because the tenant wanted it right beside it. So I think from that question would raise the point that could we ask for more adaptable clients as well in terms of do we really need to can't we work around certain constraints, and rather than having to adapt the structure, can't we come up with more logical requests from a client?
But I think the reality though in buildings is that that's just not going to be easy, is it? Building owners change, rapidly sometimes. But adaptability surely has to be a key. I'm interested to take us back to the question which Ed left us with about the use of data and monitoring sensors and actually use of actuators and things. I mean, how close are we, do we think, around the room to structures? We've seen sort of experimental cases, but how close are we to structures which could actually adapt their geometry or adapt something to respond to real-time loading changes or whatever else, environmental changes? We've seen it on the screen, the sun screen you showed us. We know with examples of sort of, as I say, experimental things, the footbridge, which some of you will know about, Janara, who's not here, where you have a bridge which had structural actuators in. Anybody else seen or is working on any of this stuff? No. Ed, how far away are we? I know you've been looking at this. What sort of things do you envisage? Put your crystal ball gazing on and tell us where we're going.
So another which is a research study at Technical University in Berlin to put some damping into a very, very lightweight ribbon bridge, for example, where they have a system, a pneumatic kind of muscle built into the balustrade that kind of contracts to damp out the vibration. So that's something that is it's in a lab, but it could easily be a real project. I mean, I think, you know, for example, things like dealing with settlement in foundations. If you have a conventional sort of, you know, regular column grid building, rather than designing your foundations or your piles to be twice as long to deal with long-term settlement, you know, why not put all of your columns on jacks with actuators that can compensate for the settlement over time? For example, we put buildings on bearings to in some cases.
Certainly it's been used in mining areas from quite a long way ago.
Yeah, so I don't know. Yeah, I can't think of an example where that's happened. But it's not too far off, I don't think.
I mean, I see it certainly coming in Bridge World, and in sort of structures which have, if you like, a relatively defined behaviour. But I mean, I think a complex three-dimensional structure is much more difficult to imagine. Certainly, we've played with them in bridges for a while, but I have to say, I think there's something interesting there. I mean, I don't know if you're interested to see, in case any of you haven't seen this. Come here. It's not going to work, of course. Here we go. The laptop. Ignore me. Just we'll carry on. I shall leave that. I was going to show you the John Irish Bridge, but never mind. We can come back here. I just want to project this.
Get blinded, aren't we?
Okay. Well, it'll come in a second. Okay. So the whole question, this feedback loop, I think, is interesting, and we'll certainly be wanting to do that to see how we can get structures to perform differently. Let's go back to the energy question, because I want to hear some more about that, the question from Michal. Sorry, there's a question there. Sorry, I was going to go where you want to go first, and we'll come back to energy.
So just, about the data that Ed was talking about, I mean, we can gather a lot of data and educate ourselves more about how we can improve our structure performance and design and everything else. I just wonder, should we be looking outward a little bit more and beginning to educate others about performance and what's appropriate? Because everybody thinks they know how structures should behave, and they conceive their own idea of serviceability and what's right. Whereas we know, actually, you can relax the standards a little bit. So I think, as well as looking inward and at what we do, should we be looking more externally and begin to educate the users of our buildings about performance and behaviour? You looked at the idea of the thermostats. Everybody knows what's hot and cold, and everybody has a different definition of it, and they can adjust that. But they have a fairly fixed definition of about vibration and things like that, for example. The second point is about the airplane wing, coming back to Ed's slide again. People understand that moves, but their expectation about maintenance is very, very different to what it might be in a building. So again, there's an education piece there as well about maintenance, and I think we might need to look beyond just our industry to bring people on this journey with us. So,
well, that's a very interesting point. There's several issues there. I'll come back to the maintenance question again. I don't know if any of you want to pick up.
Well, I don't know if Ed does, but I just got one point, and that's to do with simulation, because while you might think that these vibration criteria, for example, are well defined, if you try to explain to a client what a response factor of 8 or 10 feels like, you got no chance. And even if he thinks he understands, and even if you think you understand, the reality is it's very, very different depending on the frequency, which not even designers realise. So if we can simulate, if we can take people to monitor the structures and show them, well, this is what it feels like, that will help.
But we are getting to that point.
We are, yeah.
So people can simulate hot and cold. We can simulate vibration, for example.
Yeah.
So shouldn't that become part of what we do as part of the education?
Yeah. And I think that's also an area where the kind of observational method can work too. I mean, we've designed a number of bridges and structures where we might be, on the limit of what might be deemed best practice for the code in terms of vibration, where we have a plan B for how we would add additional damping later, but we build without and see if anyone complains, frankly.
If I may pick up the one thing. Definitely, in my mind, there's a label which I found in one of the buildings in 1907 or 8. There was a label on a door which which said that you are not allowed to load the room more than 150 PSF, so 150 pounds per square foot. So that idea was 100 years ago. And that thinking is that we know more about structures. We know more about how the structure behaves. We know lots of different things. And the key thing is, I think, how we can implement this what we learned from the past. So this idea about loading was, as I mentioned, in 1893. The first researcher who picked up this topic was 120 years ago, and still we are not learning anything about from this. So how we can learn from the experience? That's for the last 100 years we didn't change anything. I don't know. That is my small conclusion.
This question of perception is really key, isn't it? I mean, you put your finger on it, one or two other speakers have as well. I'm not sure how much it's educating, but it's certainly about influencing perception. We all know that if you walk across the Algaard Bridge, the sign saying "Treats Brake Step" is still there, partly because it's a bit of a tourist attraction. They don't need to do it anymore. But we know that some people will feel the wobble of a bridge more than others, and some will feel more comfortable than others, and so on. And in fact, we've very regularly, on some of the footbridges we've designed, said to our clients, look, don't waste money on dampers. Just put a sign at the end of the bridge, say this bridge moves. And it's cheaper than spending money on dampers. And it's just about perception. And I think we need to be educating our users about what is an acceptable feeling of floor movements, for example, if people are walking along the corridor.
But the problem with perception is it varies infinitely.
Well, it does. And I think, you have to deal with the fallout when you get complaints from somebody.
I do.
And we can say, well, it doesn't matter because it's not a problem, from the structural point of view. But I think there is a big issue there. There is a loop there. I think this comes back to the whole question about monitoring, feedback information, making sure people learn from the real world, which is what I wanted to come back to, the question about maintenance. So you were talking about the aircraft, which are routinely maintained in a way that is completely different to what we have in our sort of perception for structures. And yet, what's that about? That's about educating the public about the level of checking and maintenance that's going on. In this country, we're blessed with a system for our bridges. I'm going to come back to bridges since we've got our client here. That actually means that they're all inspected and maintained routinely and regularly. We know that the collapse in Italy, maybe there's a different regime going on there. And you could look around the world where that's not the case. And therefore, the problem is perception. People think that, help, is my bridge going to fall down? So we need to educate the user as much as ourselves as designers.
Even explaining things like why we actually do inspections. It's amazing that people say, oh, you've got some lanes off on a bridge. Actually, we want to go and do some inspections, and we have to use sort of means. So we sometimes use car analogies and aircraft analogies, but we need to inspect and maintain our infrastructure.
Let's come back to the question of designing for serviceability or not. In other words, do our structures govern our government? In fact, just coincidentally, yesterday I was listening to a presentation on FRP structures, carbon fibre and glass fibre structures, which are absolutely designed for serviceability. They're designed on strain limits, usually 0.2% strain or something is the limit. Your carbon fibre or your glass fibre has got a linear strain curve, there's no plateau, and in terms you've got way more strength than you could ever use because your limit is to do with the resin that the carbon fibre or the glass fibre sits in. You don't want that resin to crack. So you don't do ultimate limit state checks. completely the opposite to, I mean, you probably do a couple of checks, but, you know, just to satisfy yourself that you have got enough class in there, but by and large, you are you're stiffness driven. What else? Where else do we find? So I would disagree with Will on that score.
Yeah, well, if I could,
where else do we find that happening?
I slightly disagree with you as well. I mean, so if you say it's a strain limit, that's not a stiffness problem. That is just that your strength limit happens at a very low strain, or you're not allowed. It's like an old stress design.
It's not an ultimate limit state problem, because we've got plenty of extra strength for an ultimate limit state condition. Ultimate limit state being, after all, the collapse condition, the moment of collapse. What we're concerned about in those structures, and I was interested to know where other structures, and I think probably in some concrete structures we'll find it as well, where, you know, for durability reasons and other reasons, we've got to limit the crack width, and that then becomes the governing criteria. That's what
durability, I buy. Deflection and vibration, I think, is a different set of criteria.
But isn't that serviceability? Oh, well, there's a question. Go on then. Do we agree that vibration is a serviceability problem or an ultimate problem?
Vibration.
Depends how big the vibrations are, I suppose you'd say. Now, I mean, those things tend to be serviceability limits, I think. And I have to say, I think we come across them more often in bridges than perhaps in buildings. So you may be right with buildings, until we start designing our floors in FRP. Who else has got a question they want to ask? Go on, yes, please.
Hi. Thank you for your great introduction to serviceability and also putting all these topics out there for us. But in my not particularly long career as a graduate engineer, I had a healthy mix of temporary engineering and permanent design. So I'd like to bring the topic of temporary works into the serviceability states, and also the question, if we would like to design our permanent structures to be with very high utilization in their ultimate state, then wouldn't that put greater problems on the not so broad shoulders of the temporary works engineer? And also, if you need to significantly increase your temporary works to build something, won't that have a great impact on your carbon footprint throughout the construction process?
Who wants to tackle that one? Well,
my short answer would be only by exception, not in the general case, but there might be, ground floor slabs that take heavy construction loading. Sure, that needs to be considered. But I don't think you can generalise that, and I think the impact on the building typology, wouldn't be significant.
I think as a designer, you have to think through the whole life cycle, don't you? And it's always that judgment of what's the real optimum solution. I mean, lots of the beautiful kind of Heinz Eisler, concrete shell roofs of the sort of middle of last century are beautifully efficient in terms of their material use. But when you look at how they were built, you just kind of think, you built a roof to build a roof, So I think, the answer isn't always everything working at 100% in terms of the lowest carbon footprint or the most economical or the most efficient solution in the whole. And as designers, that's what we have to think of.
Let me just see, let's see if this works. I'll just show you very briefly. That's interesting. I'm not going to do it. Why is it not project? There we go. So this is a bridge. Some of you have probably seen it before. This was at UCL when it was there. This is a very slender bridge, and it's an experimental thing, with an active control system, so that as it deflects, the computer activates some actuators so as to push the bridge back up, so effectively you get zero deflection under load. But of course, because of the reliability of control systems and all the rest of it, possibilities of power failures and all the rest of it, you can't design your structure for an ultimate condition that would then be collapsed. So you allow the thing to deflect hugely under ultimate, but not collapse. But for serviceability, it stays where it's put. And with a bit of luck, there's a film here, which doesn't seem to want to. Here we go. Let's see if I can run this. So here's somebody walking on it. You can see it slightly move as he walks. But in real time, it's being pulled back up. Oh, it's not. Okay, hold on a second. Why is that not working? Do I need to pull it across the stop that second? Come on, you can do this. It works on there, but it doesn't work on there.
Talk amongst yourselves for a second.
Talk amongst ourselves. Oh, that's all very clever stuff. But I think, I mean, this is just, as I say, it's an experimental thing at this stage, but there's, you know, and in the way of some of the stuff that Ed was talking about towards the end, I think, you know, I would be expecting to see quite a lot more of this sort of thing happening. Because, of course, the amount of material in this is tiny, by comparison with what would otherwise have been a cantilever bridge. And if you look at Will's, your balconies that you had out over the sea, you know, similar sort of thing would be possible. Well, you put a damper on the end, which, of course, is going to be done as well. We play that and run it, see what happens. Oh, you lost your mouse. Oh, that's the next slide. Oh, there's this thing going on now. That's something completely different. Let's go back to that one. Oh, that's great. Tell you what, if we come out of it and we can just watch it on there we go. There you go. You found the right one. So here we go again. So you can see it bounces slightly, but actually, where they to turn the actuators off, and you can see the actuators down here. If you were to turn the computer or something off, then the deflection at the end there would be really quite substantial. So that's all it is. It's just, I mean, a very, very simple structure. Yes.
But that kind of technology must be like expensive relative to the material required.
Well, this is a yes. So did you hear that? The question, the point was that it's relatively expensive technology. At the moment, yes, maybe. Although these are very simple little actuators, it's not particularly high tech stuff. I mean, the software is quite clever, but no, it's not particularly expensive. It's expensive, relatively speaking, at the moment because of the technology. Ed mentioned a similar system that this guy, Mike Schleich, is working on in Stuttgart, using a slightly different kind of equipment, but doing the same job. But I think it's going to come, no question. Yes, please.
But coming back to the client's perception, I think a lot of times clients perceive words like deflection and vibration as bad because they are designing or they've commissioned this new thing. And to them, new means that it's going to be perfect and strong and it won't deflect. So as soon as you start speaking about deflection, it becomes bad. So if they designed this really beautiful but slender bridge and then they saw it move like that, they would think automatically, this is bad, because they don't understand. But then if you go to a really lovely old grade 2-star listed building, like I'm working on just now, which has 200-year-old timber beams, the client are like, oh look, the beams have deflected, it's got character.
Yeah, that's right.
And so I think it's sort of perception of, you know, it might be to do with aesthetic. As design has progressed and you get into more modernist aesthetic and you're looking at clean lines, really defined sharp edges, people sort of think that as soon as you say 2 mil deflection, when they have no concept that will never ever be perceived.
Yeah, but I mean, this is absolutely. It's rather like the thing that many people sort of do public. We like to sort of refer to them in a pigeonhole like that, which is very derogatory. I'm sorry, but you know, don't understand the whole thing about risk. You know, we structural engineers are used to dealing with risk because that's what we do every day. But most people work out there thinking that they're not at risk at all walking down the street. Well, of course they are. And if they walk on our structures, they think that it's all nice and sturdy, never going to fall down amongst the Sundays. But there's a risk that it'll collapse tomorrow. They don't understand that. So perception is everything. How can we change people's perception so that we can get away with deflections that we know to be perfectly acceptable? Anybody want to offer an opinion on that? Go on then. Are you going to answer that point or something else? Just stick with that point for the moment and let's see what we move. Okay. Because I think perception is really key. I mean, because I'm a bridge man and I do a lot of footbridges, I have this just about every time. Because I like designing bridges that you know, they're not made out of masonry. You know, they're long span, they're going to move a bit. I've just been on one today, and it moves fine. So what?
If I can
Go for it.
suggestions. 2 weeks ago, I was at the shop in the city centre. Maybe not the city centre, but in Cambridge. But it was in Cambridge, and I found that while I was shopping, all the floor was vibrating, and the deflection was something like 10 millimeters. And did I care?
No.
I didn't. And I was pretty sure that the other customers didn't even notice that.
Yeah.
So the perception, when you are sitting at the table and you have a computer in front of you, you might feel slightly different, that you are just in the movement, or you move. And so what is the perception exactly?
So I can give you an example from just today. So I've got a new colleague who sits right next to me at work. We've got a suspended floor, and I'm used to it. I've been in the office for several years. I don't really notice anything. Somebody walked past today, and my colleague said, "Gosh, isn't that floor moving?" And I yes, it did actually, but I didn't take any notice of it because I was used to it.
But I think we have to live with this. I mean, there's always going to be a range of perceptions, but I think we can do a lot with our clients at least. Sorry, it was you. To our clients at least about what they can expect.
But again, I think we can perhaps learn a bit from our building services mates, because as Cormac said earlier, that people experience hot and cold differently as well, and we don't try and keep everybody happy 100% of the time in terms of those environmental conditions we try to provide in our buildings, because it would be a huge amount of energy, a huge amount of space for a hugely increased size of kit that is not necessary for 95% of people for 95% of the time, and we just accept that there's a sort of exceedance of that criteria occasionally, and that's okay. We don't have that sort of attitude in structural engineering.
Ed, what's the equivalent of putting a jumper on for a floor vibrator?
Well, I mean, there is some stuff done on that. There is, working in an office where it's all cellular, offices, and it's all
stripped out and everything starts bouncing around a little bit because you don't have the benefit of the partitions and stuff. And we designed an inflow damper, a couple of £1,000, and it sorts it out. So there are methods. You just, it's another opportunity to be creative.
And damping is always an option, and it's a cheap option. And it's a very easy. People think it's a problem.
But to Ed's point, we never think about designing it skinny down and then add the damper later on. People's perceptions change, and maybe that's where we begin to need to go a little bit about Plan B.
But it's only a tiny step from adding a passive damper to adding an active one.
Yes.
That says, oh, the building's moving a bit too much today, I'm going to switch on. And that happens already. There are examples of that. But active dampers, for a while, for a long time, were not considered really reliable enough. Now I think that's changing. So you've been dying to ask a question, so please go ahead. Or have we moved on?
No, I was just going to build a bit on clients, because it's easy for us as structural engineers to make these points, but if you're a client investing £100 million in a building, they would be scared, as I would be scared, that if a floor starts vibrating, it becomes a white elephant, that you can't rent it out or whatever. Yeah. So it's not that easy to change these perceptions, but there are real big risks that,
So what's the answer?
The answer is that we need to adapt them, but by monitoring. I think that is the way forward.
But as Will pointed out, the criteria, the acceptance criteria, are relatively arbitrary. An acceleration of whatever is an arbitrary limit, because some people will feel it, some people won't. So it is about perception. And if you let's imagine you're building with some kind of active control system, active damping system, which is responsive to what's going on in the building, that you can adjust. You can adjust, at what point do you kick in your damper to make people feel comfortable? Because you've got an old man sitting on the top floor who feels it and doesn't like it very much, so you turn up the control system slightly. Rather like you turn up the heating control. Is that the way we go? I'm throwing questions out there. Will looks horrified. Go on.
No. I think the way we don't go is by putting in twice the weight of beam.
Quite, exactly.
I think what we do is we take the client onto a simulator and say, well, this is what this is the cheapest version. This is what it feels like. This is the cost for damping if we need to add that. And what we don't advise is that you go down a heavier, more material-intensive solution.
The other alternative, of course, is that you simply, the complainant, you simply move them to a different part of the building, because often it's a localised problem, isn't it? Yeah.
Or you put up a sign that the inside is that 20% of people might feel this area bouncy.
If you buy an apartment above the 75th floor, then you're going to be moving more than 50 millimetres in your sleep. This kind of question. What I'd like to do, just bearing in mind the time, would just try to draw some things together. If anybody wanted to sort of try to sort of start thinking, well, what might be some of the futures? Ed, as we heard earlier, chairs the Structural Futures Group here at the institution, and I think it'd be really interesting to sort of say, well, look, are we just going to plough on designing to the codes and having too much material in our buildings, as Michal would tell us, or are we actually going to start being a bit more imaginative, talking to our clients about how we can be, use data, use modern technology, use something in a way, maybe start small on a small building and then go bigger. Where are we going to go with this? I would love it if in 5 years' time we sort of come back again and say, well, look what's changed. So who's going to? What are the things that we can take away, and what can Ed set a little task group to investigate, perhaps? Bit of research that's needed. Go on.
I think for me the first step has to be to encourage engineers who are inherently conservative to push that figure up from 0.8 to 1. That would be the first point. And the second one is to at least start by designing to the code recommendations for office loading and not the custom and practice of 5 kilonewtons per metre squared. And that's before we get into the arena of active damping and that sort of thing.
Well, I mean, that ought to be going back to what we should be doing anyway. I mean, in a way, designing to a unity factor and to the code ought to be what we should be doing anyway, isn't it? But it's not been common practice. So that's the first point. Active control systems? How far away are we? What could we be doing? Ed, what do we need to learn?
Maybe it's just an attitude of trying to move a bit more from kind of the lab into real projects as a starter.
I mean, active damping for servers is not at all a new thing and is used on tall buildings in East Asia. I mean, what tends to put clients off from installing them rather than heavier passive dampers is actually maintenance costs.
Yep.
So it is something, if it's a proprietary system, you're signing on to a deal where, they need to come in twice a year for the next 100 years and they charge what they like, nobody else can approve it. There are issues around the products and IP for these systems as well.
And that again is a problem because of the novelty. While there are only a small number of players and they can, as you say, can charge us about what they like, but as soon as there's a market out there, then that's going to become less and less. If you've got a tall building, you've got a big maintenance budget anyway. And
But you don't want to make it any bigger.
Well, you don't. Yeah. Were you having your hands up or just scratching your head?
I just wonder is that a little bit, like the way the automotive industry is going in the circular economy. You're not buying a car. You're per se. You're buying the ability to do mileage, and you just wonder that will the maintenance on tall buildings kind of move towards a circular economy type model, where you're buying fit for purpose damper over time, not necessarily a damper, and then buy maintenance as a separate package.
Yeah, that's a very interesting point. I think we're going to be hearing much more about circular economy thinking anyway. But yes, what's the building equivalent to the Tesla? I suppose we're sort of the really low energy, and of course the auto, what do you call it? Autopilot. What do you call this? Self-driving cars. Autonomous. That's the word I was looking for. Sorry. Yes, please.
Kind of similar to the kind of Tesla. Do you think as we kind of like push higher with things like prefabricated structures or sort of newer materials like cross-laminated timber, just by the nature of what the material you're trying to use to get that high, or the amount of R&D time you can put into something like a prefab compared, do you think there might be anything that comes out of that sort of like lessons that could be learned through that process?
Anybody want to take that? Go on,
Michal. That's a good idea. However, that technology is well known for the last couple of years. I think 60 or something, but still it's not going to, or it's not used very, very often. For example, in the UK, in the other countries, for example, Denmark or prefabrication leads the construction. In the UK, it's not very common. But definitely, I think that is the point where we can make the structure more efficient. But I would like to also add something about the energy and embodied energy in the construction. I think the strategy which is lightweighting, it's the strategy which might reduce the embodied energy. However, in lightweighting, we have the issue about serviceability. So that all the aspects are connected with each other. So, but in general, how we can use the material how we can use material where it's needed. That is the point. So not to waste material. And even in case of adaptability, so we can adapt every single building, as I'm aware of, but I think we can. Refurbishment, we do refurbishment. We adapt the different buildings for different purposes. We do that a couple of years. So every single building is adaptable. And we can do that in the future. So, yeah.
Yeah, no question. The prefabrication is something which we could do more of better. It's very common in the British world, but less so, I think, in the building world. But I think those who are doing it are clearly in the vanguard. And the other thing, of course, one can do much more easily with that is to embed the data, sensors, and gathering information that more reliably. I'm going to pull. Sorry, go on.
A couple of things just from me, things that haven't come up really. One is about digital design and what impact that has, and it's certainly coming in the bridges world. So that's just thought. The other one, I do worry about Michal's sign that he found on his building about the loading, because we certainly have thoughts always around compliance, and managing, in the longer term, that the things that are being complied with. Not very far away from where you're doing your bridge in Milton Keynes, Ian, a vehicle, a lorry, went straight through a bridge deck on a bridge that was clearly not designed in any way, shape or form for vehicle loading. It was a footbridge, and this vehicle that was part of an event actually decided to drive over it, and there's a picture in the local papers in Milton Keynes with it.
But of course, the bridge situation is very different in that sense, because once the vehicle's on its way across the bridge, you can't do anything about it. Yeah. But in a building, it's very different. If you're monitoring your load, you're monitoring the load on your floor. You set off an alarm, and people you can get them out. Yeah. You can actually do something about it. With a bridge, it's very difficult. What I'm going to do is just to try to wrap up. I'm going to give you each a minute or two to say your sort of parting shot. I'm going to start at this end with Neil and go down the row in case there's anything you want to add. But otherwise, I think we'll wrap up. Unless, again, so if there's anybody else burning to say something. But let's start with you, Neil. Anything else you want to say?
I think that was my parting shot.
Okay, good.
A couple of areas that I thought hadn't been covered earlier on. So.
Very good. Michal.
Yeah. Now we are looking at what does mean good performance for the service. So therefore, we would like to find some kind of maybe some kind of benchmark in case of material use in the buildings, or how far the current buildings are from the ideal buildings, or how we can make it better in case of use less energy. So I think that having some sort of measure, either it's CO2 emissions equivalent per square meter, which varies between 550 to 1,950. I checked yesterday in one database. So it's totally incredible how it varies. So I think having some kind of metric, or having the kind of benchmark, we can put our building somewhere and to find, that is the building which might be good, might have good performance for the service. And we don't have that kind of database or that kind of benchmark. Okay. So maybe some sort of that. And that benchmark might show you what material might be used, how the structure elements might be shaped, what the spam should be like, or something like that. So in the very beginning, to have in the mind what the best solution might be for the service.
Okay, that's very useful. Thank you. Will?
Yeah, well, just to say a little bit more on that. So there is some of this data. So in the tall building industry, especially internationally, there is a lot of focus on the kilogram steel per meter square, which is a very simple measure. that you are, held to account. How is your building performing? Why is it high? How did you make it so low? So there is something there. Kilograms, meters cubed per meter squared of concrete as well. Is another measure. But I don't think it's as widespread as it should or could be.
Sorry to mention, yes, when I've conducted lots of different interviews with the structural engineers, every single company has their own benchmark, has their own knowledge about something, like what should be like for what load, what weight of the square meter should be like. But it's not available to publicity, and that is the point where we like to have some kind of idea.
I think monitoring is a pretty low-hanging fruit. If we can monitor columns in buildings, not just floors, we can actually see how far off are we the loading that you were showing on your slides there, and you can alarm that as well.
And just around the room, I mean, is anybody doing that? Anybody doing any work where they're actually getting monitoring instrumentation into buildings yet? We're doing it on bridges quite a lot, but is anybody doing it in the buildings? Apart from these guys on the front. Okay, so that's interesting. Nobody. I would be surprised, actually, if we was to get with a bigger audience. I would hope to see some hands go up, because I'm sure this is happening. Maybe we're a bit behind the curve here in the UK.
I think it's happening for dynamic loading much more than for static loading. So seismic monitoring,
because it's,
monitoring.
as you say, it's low-hanging fruit. It's easy to do. We do it in bridges all the time. You wouldn't conceive of doing a long-span bridge these days without a sophisticated system. Yes.
I wanted to make is, once we have that data, what do we do with it? What is structural engineer? What are the skills that we need as structural engineers to be able to do that? Point. Should we be doing probabilistic assessments on all of our buildings?
It's a very interesting point, and that opens a whole new debate, which we don't have time for. But you're quite right. When you start generating really stupid numbers, amounts of terabytes and sort of gigabytes and whatever you call them.
Can I have one? I'll say then.
No. Yeah. Go on. You've had yours.
No. So my slide that I cut out was data, information, knowledge, wisdom.
Yeah,
and it's
that's right.
converting it through to that wisdom. And okay, I'm looking at it from a particular perspective from structures, but it's actually getting to that point.
Yeah.
As you say, terabytes of data, but it's actually converting it into something.
It's a whole new area, not a new area. It's a big area. We've been doing it for a long time. But you're right. There's a whole science around the interrogation of live data, because you can't store it really. There's too much of it. But anyway, Ed does get the last word.
Sorry. So I guess for me, it's sort of incumbent on all of us as designers or owners of structures, but designers particularly I'm thinking about, to improve the efficiency of our design. There are lots of obvious drivers for why that is imperative for us. And I think I've really enjoyed this. It's been really a sort of rich and varied discussion, and we've discussed some really simple and kind of low-tech ways that we can do that, and we've just discussed some really complex and high-tech ways that we can do that, and what's appropriate for each project will be different, and I think we have to do what we can to push, to the edge of what's appropriate on a project-by-project basis, and the most important thing is we should actually think about it rather than just do the next project the way we did.
Exactly right. Exactly right. And yes, we're pouring you to educate some clients. I rather like that one along the way. Thank you so much for coming. I hope you found that interesting. It's gone away. You got away with some stimulated thoughts. Take it back to your offices, your places of work, debate it, discuss it, develop it, because I think there's no doubt that we're going to see much, much more of this kind of stuff in the few years to come. Thank you to our 4 panelists. Thank you so much for them. And thank you to David for getting us all here today, for organising this. Fantastic. Thank you very much.